Okay, this video is going to be just generally graphing the exponential and the exponential equation and what does everything mean or what does everything do. So generally, when you have an exponential, it will look like this. Now, granted, this is the most basic form: y equals a times b to the x, the most essential form. And so a stands for how much stuff you start with. B stands for growth or decay. So I like to say starting stuff generally. And to be more specific than that, even if we're just talking strictly a graph, A is your y-intercept. Okay, so that's kind of nice. B is your rate of growth or decay. How much are you growing by, or how much are you decaying by? So rate of growth or decay. So that is generally the exponential function, also called a geometric sequence. So if you do geometric sequences, you'll have something like this: a sub naught r to the nth power, or something like that, or r to the n minus 1, or that geometric sequences are also exponential. So if you ever get into those, that's a place where they connect. But anyway, that's beyond the scope of this thing. Let's just graph a few of these and see what's happening. So let's say you have y equals 2 times, and this number 2, I use 2 too often. Let's go with 5. Probably use it too often too. And we have something that's going to triple in value every day, and we'll have x as days or something. So y equals 5 times 3 to the x. So if we were to graph that, maybe you don't know how to graph these at all. Again, whenever I don't know how to graph something, I just like to plug in numbers, kind of like guess and check. Just go in and see what's happening. And I pick some negative values, so maybe -2 and -1 and 0 and 1, 2, 3, 4. You could get outlandish after that. But if you start with these basics, that will at least get us a start of what this graph looks like. Okay, and I pulled in a little graph paper here. And what I want to do, because I think this is kind of worth reviewing some of your rules of exponents, is show you the work on this. You can pull out a calculator and plug it in, but let's see, this negative exponent part might throw you off a little bit. So to get y, you'd have to go 5 times 3 to the -2 power. Well, when you do that, 3 to the -2 is a negative exponent, which moves it down. So this is like saying 5 times 1 over 3 squared, or 5/9. So we know that is 0.6 repeating. So let me erase that. Or 0.5 or 5/9, 0.555, which would round to approximately 0.6. Okay, same with this one. 5 times 3 to the -1. Well, 3 to the -1 moves it down, and so you have 5/3. Or approximately 1 2/3, or 1.7. I'm just going to approximate these so I can just get generally what the graph looks like. 5 times 3 to the 0. That one, in general, 3 to the 0 is 1. Anything to the 0 power is 1, is 5. And then 5 times 3 to the first. This one's going to get crazy in a hurry. We've got 15. 5 times 3 to the second is 5 times 9, and we're at 45 already, and I don't even care about the next two. So when we graph these, so -2 and 0.6, so we're here. -1 and 1.7, so there. 0 and 5, 1, 2, 3, 4, 5. And then 1 and 15, which already blows off our scale here, 10, it's going to be up here somewhere. And so we've got this graph, again, that has an asymptote at the x-intercept, and it flies up there pretty fast. And so that's what an exponential is. Now there's with positive growth. What happens if it's negative or if it's decay? So let's say we had this function. So we had, say, y equals, we'll use the 2. 2 times, and instead of a whole number like 3, like something that's tripled, let's do something that's cut in half each time. So we'll use, and let's not use 2. Let me go back. I changed my mind. Let's use 3. So this would be y equals 3 times 1/2, 3 times 1/2 to the x. So in this case, again, here's x and y, and we'll do the same thing. We'll go -3, -2, -1, 0, 1, 2. I kind of know what I'm doing. You might not, so those points may or may not work. I'm just randomly guessing them. This may not give me my whole graph, so you might want to try some different things, but it should. So we'll throw in some graph paper like last time and just take a look at what this thing looks like. And again, show my work so that you can kind of see what's happening. So 3 times 1/2 to the -3rd power. Well, again, negative exponents, invert your fraction. I use some pretty simple terminology sometimes, which might annoy math teachers, but it's 1/2 to the -3rd would be 2 to the 3rd power. So it flips it, and then it changes it to a positive. So this is the same as saying 3 times 2 to the 3rd power. And so 2 to the 3rd power is 8. 2 times 2 is 4. 4 times 2 is 8. 8 times 3, we're looking at 24. So in this case, -3 gives you a massively huge number. And then, well, maybe not massively huge, but big comparatively compared to this 1 by 1, this scale of 1 graph I've got over here. I could change the scale to anything I want, but hopefully you get the idea. So 3 to the 1/2 to the -2 power, same thing. 3, you flip it, and it would be times 2 squared. So now we're at 3 times 4, and we're getting smaller each time. So 3 times 4 is 12, and we're cutting it in half each time. And you notice that, 3 times 1/2. It should be cutting it in half. That makes sense. And then 3 times 1/2 to the -1. Again, that would be 3 times 2. And 3 times 2 is 6. We're still following my pattern. That's nice because I'm going by even numbers. Or I'm going by sequential numbers, I should say. 3 times 1/2 to the 0. Again, this 0 exponent is very important. 1/2 to the 0 is 1. So this is 3 times 1, or 3. And we'll keep working on down. 3 times 1/2 to the 1st power. That's 3/2, or 1.5. And again, we're still cutting things in half. And then the last one, we could do it here. 3 times 1/2 to the 2nd power. That's 3 times 1/4, or 3/4, or 0.75. And I think we're ready to graph this thing. So you go left 3, up 24. Well, I'm going to go by ones. I'm going to stick with it. And it's going to go way off the graph. So we'll start with 12. So -2 and 12. And even though that's way off, it's off the graph, there it is. It's a couple above my graph. -1 and 6. So left 1, up 6. Be right there. Again, we knew that my A was 3, so that's my y-intercept. Right there. And 1 and 1.5. Right there. And 2 and 3/4. Right there. And we've already got what this looks like. Wow. And again, does it go below the x-axis? Well, I know it doesn't, but make sure you convince yourself of that. Maybe put some numbers in for x that are huge. Maybe 10. That's not huge, but throw in huge is a relative term. So 1/2 to the 10th power, you're going to have 3 times a very small fraction. So uh, there's what it looks like. And notice when it's decay, notice the shape of the curve. So this is less than 1, and my curve goes down towards the x-axis when you go from left to right. If your growth is 3 or something larger than 1, notice my curve, as you go left to right, grows up. So we got growth. It's climbing. And so that's the main difference between the two graphs. And I hope this helps. Best of luck with it, and I'll see you next time.